Okay, hello everyone. This is all still like work in progress, and it's relatively recent, but I still believe that there are some really like valuable ideas in there which make like deep learning way more efficient if we take some like, pre-existing ideas from the SMC and try to integrate them in the deep learning framework. And to start with, obviously, there's like a really large literature and growing literature on deep learning methods, but they're all I think they're trying to address very similar or even identical questions to SMC and ABC methods, and that's why I believe that there's like a bit of a reusability issue in the sense that deep learning methods are not as like widely used as the classical like SMC and ABC methodologies. And the reason for this is, I think, is that simply the stochasticity of the data is like extremely large, which means that we have to narrow down our problem scope quite a lot. So and like I believe that I think that we can like address this problem by just finding a more appropriate like data representation, and to essentially address the problems of the narrow problem scope, obviously the hardware constraints and time constraints to make training more efficient. And so for this talk, then I decided to go through like the general supervised machine learning workflow for deep learning, starting with the design phase, of course, where we think about the problem we're trying to address, the simulation phase, the processing phase, and the deep learning phase. And the already underlined here processing, as I think that's kind of the key area where most of the improvements actually can be made. Yeah. So, but to start with, I'd like to have one brief excursion slide on simulations, as I think they are a bit, as there are also ways of how experiments can really go wrong if the simulations are wrong, if they don't capture the appropriate level of variance. So generally, we simulate our training data set using simulators like MS Brine. I've also done it in this study, and to simulate like, multiple levels of variation. The first one, of course, the variation of all the parameters that didn't manifest throughout the evolutionary history. And then, of course, there's another layer of variation, which is of all the parameters that did actually manifest. And there's like a really interesting paper from a few years ago about the limits and convergence property of SMCs, from which I think in deep learning we can also learn a lot. And what I like took away from this paper, that's essentially possible to generate very large or infinite data sets, which are basically entropically empty. And if you think about, for example, demographic history, and you want to capture the variation of demographic fluctuations, if they are simply too strong in your data set, it means that all the coalescent times fall into early or late time winds, depending on how strong the bottlenecks are throughout the simulation. This is kind of an obvious one, I think. And in addition, what's maybe also a bit disregarded is that the ratio of recombination to mutations is also like extremely important in determining the outcome of your simulation. If you think about the tree sequence, and there's lots more recombination with respect to mutation, meaning there's fewer mutations actually explain each tree, then the problem becomes increasingly hard. And there has been in the past already a bit talk about using, for example, standard PopSim as a guideline to benchmark models, but in the same vein, it may be even appropriate to provide guidelines for even simulations itself, or and before going to the processing stage, I'd like to go to the deep learning stage first, because I think it's relatively trivial with regards to the model choice. Even in the past, I mean, that is not really the hardest problem to choose a CNN, and in the same case, I'm just using transformers now. But just to say a few more words, I'm using one of the recent transformers libraries, which just encodes or uses the newest features like flash attention rotary embeddings and reduced floating point training and all this stuff. But essentially it comes as simple as importing the encoder from a package. So I think there's not much magic to it. Yeah, but the processing stage is, I think, more important. That's kind of how we represent the data to the network itself, and how we or what this structure should ideally be like is that it should be very small in the sense that there are just few dimensions which are relatively or which are dense in information with regards to the properties of the ancestral recombination graph. And how we achieve this smallness and denseness, I think, is to orient ourselves exactly along this ancestral recombination graph. There are at least two strategies. One is to infer the ancestral recombination graph with methods like argweaver, or TS-infer and TS-state, or other methods, and then use that to essentially train on using a graph neural network to do some inference. Or and that's the new strategy, which I'll go into much more detail in a minute, is to approximate the properties of the ARG itself. And of course, it's also like a strategy 0, which is to just use the genotype matrix or genomes themselves and do some inference. And there's like no out of distribution issues because you're really using the data itself. But it seems to be rather inefficient due to the large, like, unstructured way of how the data is simply presented. And then there's like the second strategy, which is about how I attempted it in my graph neural network paper on the beta coalescent, as I trained on exact ARGs to infer some demography. And demography here means multiple time pods in the past and not a single value, but 40 values approximately of demographic change. And the overall idea was that we'll just use argweaver or some other ARG inference method to get our inferred ARG, and then use that during inference to get our dependent variable. But this runs in an out of distribution error problem, because the inference error will just mess up the downstream neural network for the inference. And how this could be addressed simply is by training only on inferred ARGs. But since it's very costly to infer ARGs, it might only become feasible in the future. And then to go to some new strategies, which is using ARG representations. In this case, I'm using the transition matrix from SMC as my ARG representation. I'll explain the transition matrix in a moment, or how I use rather an approximated version of it. And the strategy is really the same. You simulate some ARGs, you calculate the exact transition matrix from the ARGs, and have a second network which infers some variable, which is now like a trivial problem because there's even also analytical solutions for it. So you really get perfect demographies if you only train on exact transition matrices. And then we have a first step of inferring the transition matrix itself. And this is very similar to the first talk we heard today, which is separating the problem into inferring TM-RCAs, and then using these TM-RCAs to calculate probabilities of transitioning between the coalescent states. But this runs exactly in the same problem as step 1, which is if you train on exact matrices but get only inferred ones, then there's again an out of distribution problem. But nevertheless, I have some figures at the end which generate really nice TM-RCA estimates using transformers. So that's still something valuable to keep. But the real method which I want to present here is the third one, which is actually just approximating the transition matrix and using the approximated transition matrix for training using transformer model. And the first step is simply like reshaping the data, pre-processing it, and then just having one simple training step of using an approximated transition matrix to train. And there's no out of distribution error, and it's really fast because, yeah, we'll see in a moment. To go into a bit more detail now. So how we are all used to it, we have the genotype matrix, how we get them from MS prime with individuals on one axis and mutations on the others. Here in this encoding, there's like no information about the actual position of each mutation, which actually is the real information, not necessarily so much the individual complex mutation patterns, but of course there's also some information if you think about the SFS and shared mutations across individuals. But the real information is really about the density of mutations across the genome. And the more dense an area is, the larger are the branches of the ancestral recombination graph, and the larger is also the population size at this particular part. And what I propose here is that we compress this genotype matrix a couple of steps to generate newer representations which we can use for deep learning. And the first one is actually quite simple, is to calculate from the genotype matrix a mutation density matrix, which already encodes the position of each mutation. And how I do this particularly is here I have 12 diploid samples, so meaning 24 over just two pairwise comparisons of each row. And meaning, yeah, I have all these comparisons here on the one axis. And then I just do a windowized scan across the genome, which can be very efficiently implemented. And then I'll have essentially density patterns across genomes. And what you notice here already, that I can encode very large sequences of multiple megabases, which kind of already addresses also the long context problem of transformers. If we only have here 400 400 dimensions in the sequence dimension. But to go even one step further is, because we could already train on this matrix, of course, but if we flatten this matrix into just a very long vector, and then calculate the transition matrix from it, we're simply using the mutations as a proxy for coalescent time, then we can simply see if we have, for example, in one window, like 20 mutations and the next 100 mutations, depending on how big we make our windows, then we can just fill up this matrix by going on the one axis in which bin the 20 falls and on the other axis in which bin the 100 falls, and then we'll add just +1 in this particular window. And then we do this for all these values here. And then we have a very dense like transition matrix representation, which is just rescaled to get the coalescent times. So we see it's really a compression process from left to right with the aim of incorporating ARG properties directly. And there's, of course, then a trade-off, because you need more. The more you compress your data, the faster the training will be, the less parameter you'll actually need. And also, the more accurate it is, I find. Yeah. To go into a bit more detail, of course, if you have the exact like transition matrix, how we get them from ARGs, they look different than the approximated ones, as I'm literally just summing up the mutations here, which is skipping any kind of neural network-based TM-RCA inference, which I don't think is necessary for demography inference. Yeah, and then we'll have essentially train with the inherent error of the inference, quote unquote. And these are the kind of demographies I train on, which are just random steps across the population time. Yeah. And a bit more intuition on why this actually works is, if here just a different mutation density matrix, which is log scaled. So the same as before, but just a slightly different data set over 10 MB with 10 KB windows. And if the row over theta, so the recombination to mutation ratio is somewhat favorable, then you see actually direct correlation between mutations, TMRCA, which of course with the theory predicts as well. So that's kind of why it actually works. To show also some results on real data is here we have from an SMC paper, ESMC, which inferred the demography of Arabidopsis thaliana under in addition to selfing and also dormancy. And I just use also some Central European Arabidopsis samples. And here I essentially get with in a very short amount of time, also very good demographies. And if I use like the MS or the standard POPSIM parameters, which is very favorable in terms of recombination to a mutation, then literally is a process of 2 hours, including simulation, preprocessing, and training to get nice demographies. If I actually use the real recombination and mutation of from Central Europe, then it's actually a much harder problem, because there you have only about 0.2 mutations per coalescent tree, so there's much more recombination than the training just increases. Yeah. And I'd like to highlight here also that I don't use an external GPU or anything or GPU cluster. Like all this was done on a laptop. Yeah. And here's also the benefit from this kind of empirical use of the transition matrix is that you can decide what you actually want to do. You have the option of just using a single sequence, but a very long sequence, and then you're doing inference like PSMC. Or you want to focus on very tiny genome fragments, like 100 kb, for example. Maybe it's not so tiny, but it's relatively small to what's traditionally used for SMC methods, but increase the sample size a lot, and then you can infer demographies. For example, the case of Arabidopsis can infer 30 demographies for the first chromosome of Arabidopsis. So here in this case, we just still need to figure out a bit. It's shifted on the y-axis, which I believe is due to rescaling of the very strong selfing in Arabidopsis. But it's nice, the shape is still valid for real data. And yeah, before concluding, I'd like to highlight a few features of the transition matrix itself. And as I put it into the transformer architecture, which I can make relatively small now, it's really a nice property, sorry to go back, is that we have here features of 32 by 32 population times, which means the context length of the transformer is literally just 32. And that's compared to language models where it's often thousands context lengths, it's really tiny. And that's why it works even on laptop hardware. Yeah. And yes, so yeah, to give a bit of a summary at the end, what I said before, that's really important to think about carefully, that the simulation data set actually contains any information. Like I aim to have a very small, or I think it's very favorable if small, like theory-oriented summary statistics, which are like neural network friendly. We don't have to go, of course, all the way to the SFS or LD, but I think somewhere in the middle between the genotype matrix and the SFS, there are probably lots of really great summary statistics, which may even capture also long-range interdependencies, as we are much more flexible in actually designing the transition matrix. It was just like a first attempt. And then, of course, the out-of-distribution error is also something which needs to be thought of if we go the direction of inferring ARGs as a first step. And then I'd also like to mention again that the models I'm using are actually not that small. If all the appropriate steps, like using the accelerate library of Hugging Face, are used, then you can actually get even hundreds of millions of parameters to use on laptop hardware. And just to end with a few nice results, which I thought are a bit would be a bit of a shame to just throw them away. These were from one of the methods where I tried to infer the transition matrix itself using a transformer. I compared, if I want to infer it directly, then I also had to do get a TM-RCA estimation method, like we heard in the first talk. And I compared the transformer method just to Tier's infer and Tier's state. And I see that the variance essentially is smaller for this coalescence transformer model. I think that's a nice result, even though I didn't need inference because I just summed up my mutations to get my approximated transition matrix. And the last, or one of the last results is also that I can do, or that's possible to do a TM-RCA inference along the genome. Depends, of course, always on the ratio for rho over zeta, but here it's also possible. The only issue I still haven't solved, but there were some nice ideas in the first talk, is on how to discretize the time windows here, just infer TM-RCAs in bins, essentially, which I think there are much better ways probably to just to define the bins first and then do inference. And lastly, a bit of an outlook. I mean, I've worked already on the beta coalescence graph neural networks. And these models, if you look at the LD, like become quickly very chaotic. On the left, you have Kingman, and here we have beta coalescence, which gets stronger. And here, I mean, the Markovian or approximately Markovian property of the Kingman coalescence gets completely ruined. And for that, I think there's maybe some creativity needed to define neural network appropriate transition matrix like summary statistics for these complicated coalescence models without the need of inferring like whole ARGs, which are in most cases or all cases not designed to handle beta coalescent models. And yeah, these are just some references. Yeah, thanks for your attention.